continue talking about generalization.
Thanks, okay. All right, so I just want to recap a few of the topics that Sasha covered this morning. The motivation, I guess, for uniform laws of large numbers. So remember, and to remind you of some of the notation that we're using. So remember, we're talking about restricting our attention to a class of functions f. We have some sort of a choice from that class, which we denote f hat n, that's based on the sample, the x1, y1 through xn, yn. And the particular choice that we're considering here is when we minimize the empirical risk, so the sample averages of the losses. We're using this notation Pn of the loss, which denotes the empirical distribution over these xy pairs, right? So the sample average. And we're writing this kind of operator notation, the David Pollard notation, you know, Pn of L. We're interested in this sort of choose Fn hat from our class F in this way, and we want to know how close we get, how close the population loss is to the best we could have done, given that we're restricted to choosing functions from the class F. Right, so it's this difference we care about, and you remember that, of course, there's an approximation error term there. You know, if the class is small, then maybe L of F sub F is pretty terrible, right? Maybe the best performance we can expect from a perceptron is hopelessly bad. We're sweeping that under the rug. That's a separate piece, right? And just interested in how closely we approximate the best in that class. And we saw that we had, you know, the expectation over the sample of the risk for this empirical risk minimizer versus the best in the class is upper bounded by this expectation of the deviation between the expectation of the loss for that empirical risk minimizer versus the sample average. Okay, and we saw that we could think about this kind of quantity. Of course, we have to be careful. You know, this Fn hat is chosen using the data, so it's chosen to minimize this quantity, so of course it's going to be biased. One way to get over that and understand, you know, what sort of deviations we should expect on the right-hand side, and therefore what sort of upper bounds we can get on the excess risk for our class capital F, is to work with uniform bounds on these deviations, right? Look for look for properties of the class that ensure that the maximum over the class of these kinds of deviations between expectations and sample averages is not too big. Okay, so you know, this really is an inequality. We'll see some cases where it's a tight inequality, but it's an inequality. Keep that in mind. We're always getting upper bounds here. And then there's this nice empirical process story. To simplify things, we're going to step a little bit in the abstract direction and say, okay, we know there's an underlying loss function. We're talking about xy pairs and so on. But we just want to consider, you know, this is the set of xy pairs. This is the class of loss functions, right, mapping from xy to the loss that's incurred when you use f to predict. So we have a class of functions on some domain, and we're interested in when expectations and sample averages are uniformly close across that class. Okay? So, you know, this is the broad topic that we're working with here. And there's this really nice cartoon that Sasha put together and showed us. We think of this axis as being all of the functions that we're considering. This is the population case, right? The expectation of the loss that's incurred when we choose one of these guys. This is the loss corresponding to the function in the class. I guess this is all functions. So this is the Bayes prediction rule, and this is the Bayes risk. And you know, there's the empirical version of that. We take sample averages on our sample of size n, and if we minimize that, or there's another sample, if we minimize this empirical quantity, we may end up with something that looks really good on the sample, but actually is pretty terrible in terms of expectation, and if instead we restrict to, wow, it's hard to see that. If instead we restrict to this to a limited family, then we may do much better. We may be able to show that, you know, uniformly across that family, sample averages are close. I guess even for this family, they're not that close, but it's a cartoon. Okay, so that's the picture to keep in your head. Let's get a little more precise. So we're talking about a class of functions, G, defined on this space they're functions that map to a bounded range. I guess that's not, that's going to be important when we, yeah. So we're assuming that these functions are bounded. You could relax those assumptions. We have a sample of size n, and we're considering something that's identically distributed, and we're interested in the worst case over our class of functions of deviations between expectations and sample averages. We write that using this notation. So P of G means the expectation under the distribution P of this function. Right? Pn of G means the expectation under the empirical distribution. Right? The one that assigns mass 1 over n to each of these, Z1 through Zn. And the deviation between those two, we're maximizing over the class. Okay, so we use this norm notation and empirical process sort of notation. So, P minus Pn, we're thinking of as this operator that acts on functions. You evaluate it at a particular function, you get this deviation. And then the norm with the subscript G is saying what's the maximum over that class of these deviations, right? Evaluated at some particular G. So this empirical, we're interested in when this quantity is going to 0, right? As the sample size grows. And that's called the uniform law of large numbers because we're maximizing across the class. If there were just a single function, it would be regular law of large numbers. And we're wanting to make it uniform, looking at the worst case across all of the functions in G.
So, quick question. So
yeah.
All this abstraction, what's the randomness left in U?
The randomness in U. So if we look at it here, that's deterministic, right? That's just an expectation. This thing involves the random sample Z1 through Zn. Right, so this is a random variable because it depends on those Z1 through Zn's. And often we'll be concerned with expectations. Actually, we'll make some statements about high probability bounds as well. But to say that actually these things are with high probability close to expectations, all we're really going to focus on is expectations. There's another layer there that we're kind of sweeping under the rug. Is there another question? Okay, so a little more terminology. We say that this class is a Glivenko-Cantelli class for a particular probability distribution if this supremum across the class of deviations between expectations and sample averages converges to 0. So so we have all of the notation on one slide. This is a probability distribution on Z. We see a sample of size n drawn from that probability distribution. That sample defines the empirical distribution, which puts mass 1 over n at each of these sample points. We've got our class G of real valued functions, I guess bounded real valued functions on the set Z. And the empirical process here is Pn minus P. So it's a stochastic process indexed by a class of functions. A function that takes you from a random function that takes you from functions in G to real numbers. And we're using this norm notation, the maximal deviation between expectations and sample averages over the class G. Okay. So we're going to use that sort of notation. We call it a Glivenko-Cantelli class because, this is a Glivenko-Cantelli theorem. The result that they proved was for a special case of one of these uniform laws of large numbers. It was saying if you talk about a cumulative distribution function for a random variable, that's f, right? So that's the probability that the random variable, so f at a is the probability that the random variable is less than or equal to a. Right, so it's this function that increases from 0 to 1. F sub n is the corresponding empirical quantity. So instead of the probability that it's less than or equal to a, it's the proportion of a sample of size n that's less than or equal to a. Right, so it's a step function, right, rather than some nice cumulative perhaps smooth cumulative distribution function. Right, that's written out here. And if these Z1 through Zn are IID with a distribution that has this CDF, capital F, and this is the uniform norm, right? The supremum across all real t of ft minus, up here it's ft minus fnt, then this thing is saying we want our empirical CDF to be a uniformly good approximation of the true CDF that generated these ZIs. That's a special case of a Glivenko-Cantelli class, where the class here is these functions are the step functions, right? Parameterized by the real value alpha. Okay, because we're interested here in the sample average of the indicator for being smaller than t, that's smaller than some real quantity. So if we can say uniformly across this class G, we have expectations close to sample averages, that's exactly the Glivenko-Cantelli theorem. So that's where the GC terminology comes from. And for this special case, that's a one-layer neural network with one input and monotonicity constraint, positivity constraint on the parameter. Okay. So obviously not everything is a Glivenko-Cantelli class. So for instance, if we consider the class of indicators for being an element of a particular finite set. So for every finite set, right, every finite subset of the reals, this defines a function that maps to 0 or 1. But that's certainly not a GC class. We don't have a uniform convergence of expectations to sample averages. If you fix one of those functions, for every probability distribution, you have a law of large numbers, right? The indicator for one of these sets, the probability that you fall in that set is well approximated by the sample average as n gets large, but it's certainly not true uniformly. For instance, if you have a continuous distribution, then this expectation is 0 because you're hoping to fall in this finite set with a continuous distribution, but the supremum, right, over finite sets of the empirical, the sample average is 1, right? You just pick that set to be the set that you saw on the sample. So we always have a big gap between these two. So there's a law of large numbers, but there's not a uniform law of large numbers. Okay, and that's because this is just too large, right? This is a set of functions that's too rich. Okay, so what's not too rich? Well, there's a notion of complexity that really tells the whole story. We'll see that uniform convergence is equivalent to a property of a set defined in terms of these Rademacher averages. So let's get some, it's quite an intuitive idea. Let's get some intuition about Rademacher averages on a finite sample. So rather than functions, let's think about subsets of a bounded interval, a cube, right, in n dimensions. So think of that as, fixing the sample, let's say Z1 through Zn, and considering functions restricted to that, so they're just vectors in Rn, right? And for those function values that we see, we're going to think of them as, a subset of Rn, and we're going to measure the complexity or the size of that subset by the average length of a projection onto a random direction. So our random direction is given by this vector epsilon 1 through epsilon n. These are symmetric, independent plus minus 1 random variables, Rademacher random variables. And we consider this Rademacher process, which is a function that maps from Rn to the reals. So given a vector in Rn, for instance, one of these guys in our set H, Rn hat of H is 1 over n times the inner product between H and this random direction. Okay, so we're saying, this Rademacher process is picking a random direction and seeing how much it lines up with H, right? Sort of that, in an average way. We scale it by 1 over n. Okay, and we're interested in the taking the supremum over the set of how much we align with that particular H. and then, on average, what's the expectation? This expectation, of course, is over, we're fixing an h. This expectation is just over the epsilons, right? So we use this notation to say conditional expectation where you fix everything else and just average out over the epsilons. All right, so these are the Rademacher averages. And the intuition is, if h is small, then somehow, pick a random direction. You're not going to be able to find anything in h that lines up with that particular direction, right, in Rn. Where small means, not filling out much of Rn in some sense. Okay, that's the hand-wavy intuition. We'll go through a few examples. But let me pause there for questions. Yeah?
What is special about the Rademacher random variables as opposed to, say, uniform on the sphere?
Good question. Nothing special. They're convenient to work with. Right? We could work with uniform on the sphere, we could work with Gaussian random variables, and you can relate all of these things. Right? So in particular, you can relate them because, for instance, for uniform on the sphere, you have a symmetry property. For Gaussians, you have a symmetry property. You can split those random variables into a product of a plus and minus 1, like this, and then a direction, a random direction, I guess, scale as well with a Gaussian. And they're related to each other, right? So there's an analog of these Rademacher averages in terms of Gaussians, called the Gaussian averages and Gaussian complexity, and it's closely related to the Rademacher averages, bounded by a constant on one side and a log factor on the other side. Similar story applies in the case of spherical, and I haven't worked it out, but I would guess in that case you'd get a constant on both sides. It's got to be true. Homework exercise. Right, so that's a good question. There's nothing special, but these are kind of convenient to work with. Any other questions? Okay, so let's think about a few examples. So let's think of our set in Rn as being just a single vector. H0 points this way. And now we're interested in the Rademacher averages, the expectation of the H in that set that maximally aligns with an epsilon vector, right? A random corner of the plus minus 1 cube, right? So because we're putting the absolute values in there, we're just saying, you want to know what's the average alignment between a fixed direction and this random vector. We get something it's not 0, but it's close to 0, right? It's like 1 over square root of n. Okay, the expectation without the absolute values, of course, is 0, but we've got absolute values in there. We get something that scales like this. If we've got, on the other hand, something that's kind of n-dimensional, in particular the plus minus 1 n cube, the hypercube with this symmetric thing, plus or minus 1s, then of course, you give me a random epsilon vector of plus minus 1s, I can align with it perfectly, right? The inner product is n, we divide by n, we get 1. All right, so this one's nice and small, this one's really very big. And the right intuition to have is that this is sort of filling out the whole of that n-dimensional space. Okay, this one is not, it's pointing in one direction. More generally, if we have a cube like this that's somehow embedded in our set, H, right? If contained in H, there's, centered at some vector v, there's a little cube of scale c somewhere there, right? Then that's good enough to ensure this sort of behavior. We get a constant appearing here, right? Constant's bad, we want something going to 0. So we get a constant appearing here, or at least a constant appearing here. Who knows what else is going on in H. But at least that constant c appears. So there's some sort of n-dimensional behavior embedded in this set, right? This is the witness to that n-dimensional behavior, and that's why we get this sort of behavior. Okay, see if you're awake after lunch. So what happens if H is the all ones vector together with the negative of that vector? So all ones and the negative of it. So what do the Rademacher averages look like in that case? Exactly the same as the first case. Great. Right, because having 1 or the negative of it, we had absolute values in the definition here anyway, right? So if you aligned with This one, the absolute value means you're aligning just as well with that one. It's no different from this case, actually. All right, and you know, actually we'll see, I think it's on the next line. Right, so if we have a finite set in general, we get that 1 over square root of n behavior, and the scaling is like the log of the cardinality of the class. No worse than, I should say, the log of the cardinality of the class. Okay, so that's an upper bound. The upper bound can be really loose because, you know, these things could be very similar in some way. We're not taking account of kind of the overlaps that we see in the elements of this class. You know, and certainly we can come up with infinite classes for which this is a terrible bound. You know, we have a nice small value of the Rademacher averages. Let's look at a couple of examples like that. So think about our subset of Rn being a unit ball in the P norm, right? Let's just say 2 norm, right? So we're considering all vectors in Rn that have, let's say, 2 norm, no more than 1. Then the Rademacher averages in that case, I've written it out explicitly here, right? It's the 1 over n times the expectation of the maximum over this class of the alignment between an epsilon, between a random, this plus minus 1 direction, and a g. You know, this maximum, of course, is achieved when you set g to be the epsilon direction, or the minus epsilon direction, and then scale it back to have unit norm. All right, so calculate that. You get just the norm of that epsilon vector, which is square root n. So we get a 1 over square root of n scaling in that case. Right? Just like we got when h was of cardinality 1. Okay, so this is a nice small class, but it's infinite, uncountably infinite. So, you know, certainly taking the log of the cardinality of that set gives us a bad upper bound. Okay, and you know, you can investigate other unit balls in other norms in the same sort of way. Okay, so what do they have to do with this problem of uniform convergence, uniform laws of large numbers? So we're going to consider the subset of Rn to be the set of vectors that we get when we evaluate functions in our class at z1 through zn. Right? So consider, you know, our vector of length n is, for every function in our class we get a distinct vector, and the components are that function evaluated at z1, z2, all up to zn. All right, so for that thing, you know, and here's a nice picture that Sasha drew. Right, so we have a bunch of functions here, and we're considering the vector of values of those functions at all of the different points that appeared in the sample, z1 through zn. And you know, that gives us for each function a particular vector of real values, and we're interested in the Rademacher averages for that set of vectors in Rn. And okay, so if we fix those z1 through zn, you know, and consider the Rademacher averages of those things, where h is that set on the previous slide, right? G evaluated at all of these z1 through zn's, then we, you know, this empirical Rademacher process, it's a data-dependent quantity because it depends on the z1 through zn. We can also define a Rademacher process that doesn't have the hat. So when we're considering, you know, expectation of the supremum over functions in our class, where this expectation is over the z1 through zn and the epsilons. Right, so we can define another empirical process, the Rademacher process, Rn of g without the hat, that's, you know, same scaling, and now it's how does g evaluated at z1 through zn align with the epsilon i's. So, you know, we have two kinds of notation. This one is for a subset of Rn, and this one is for a set of functions. All right, so this empirical process involves just the epsilon i's as its randomness. This one involves the z i's as well. Okay, so that's the kind of terminology we're going to use, and it's this quantity for a class of functions that we'll see is central to uniform laws of large numbers.
Sorry, I didn't get the difference between the hat and the one without.
The hat here is I guess the definition isn't on the board. It isn't on that slide, right? And that's probably a confusing way to write it because there's a supremum over a class of functions written up there. The Rn hat evaluated at an H for some subset of Rn. So this thing is just 1 over n sum from 1 to n of epsilon I hi. And for a function g in this class G, which maps from I don't know, some bounded subset of the reals, let's just write it as R. Right, so this is a set of functions from our domain Z to the reals, and the second one, Rn of G, has two sources of randomness, the epsilon i's and the z i's. All right, so these are both random functions of something. This one's randomness comes from just the epsilon i's. This one's randomness comes from the epsilon i's and the sample. Yep. Okay. So we're going to look at proving a uniform law of large numbers in terms of these kinds of quantities. And we'll see, that the maximal deviations between expectations and sample averages are very closely related to the suprema of these Rademacher processes. And that's in expectation over what's random, and in this case, it's these guys that are random. But in fact, all these things are tightly concentrated about their expectations. So we'll focus on just proving relationships between the expectations of these things. So here's the big theorem. We should look at it in stages. There's an upper bound that says, for whatever your class, expectations of maximal deviations across that class between expectations and sample averages are upper bounded by constant times the expectations of maxima of these Rademacher processes. Right, so we get an upper bound on these maximal deviations, and given a bound on the scale of our functions, let's say they map to the interval 0, 1, then we also get a lower bound. That's like, 1 over square root of n away, and a different constant factor, but it's essentially the same thing. Right? So if you care about maximal deviations between expectations and sample averages, that's equivalent to these Rademacher processes. And all this is true in high probability, right? That because we had things uniformly bounded here, mapping to a bounded range, or you could relax that to being something sub-Gaussian and get the same rates, then these quantities are all tightly concentrated. So these things are close to their expectations. These things are close to their expectations. Everything's you can leave out the expectation and you won't be far off with high probability. Okay, so we're not going to pay much attention to the high probability part and just think about the expectation part. Okay, so things are pretty much the same. If you're caring about suprema of these empirical processes, then that's pretty much the same as caring about suprema of the Rademacher process.
So if it is pretty much the same, this means that the bounds are very tight, or are they not, and does that depend on the choice of G?
This is telling you that the bounds are very tight, right? You have this small constant factor, and something that's like 1 over square root of n. But if you stop and think about it, even g containing a single function, we get 1 over square root of n here, right? So we're getting something that's never worse than another constant factor in this lower bound, and right. So there's no room for any looseness if what you care about is the maximal deviation between an expectation and a sample average over your function class. That wasn't what motivated the study of this. This was this quantity here was an upper bound on the deviation between the performance, the expected loss of an empirical minimizer, and how good it looks on a sample, the sample average of that. Right? That was just an upper bound, and in some cases, as Sasha mentioned, in some cases that can be quite loose. There can be a big gap. There are examples, and we'll see several of them, where actually, this quantity, although it's just an upper bound, it's a tight upper bound on that other quantity, and certainly, this relationship can't be improved. This shows that it's essentially the same quantity as Rademacher average. Any other questions? Okay, so let's think about why that's true. I think it's helpful to think of this that it's really a similar intuition to what was going on. I shouldn't say that, to what could have been going on in Sasha's explanation of the performance of the perceptron algorithm, right? When you talk about its performance on an IID sample, one way of viewing the analysis, a related analysis to the one that Sasha showed, is that actually you're just swapping in and out what you call the test example and what you call the training example. And of course that has exactly the same distribution. Right? So the IID assumption means we can switch XY pairs around and it doesn't change anything. We have exactly the same distribution. So we're going to exploit that here, and that's where the Rademacher random variables come from. It's that symmetry of switching things in and out. Right? So, okay, so we're looking at the expectations of these maximal deviations. I've just written it out here, but I've replaced the expectation under P of this thing by an expectation of another sample average. Right? So, this is our sample, this with the prime, the Z1 prime through Zn prime. That's a ghost sample, and we're just averaging across it. So I haven't changed anything. It has, of course, the expectation of this average is just the expectation. Okay, but now I can get an upper bound by pulling that expectation outside the supremum. This is certainly bigger, right? No smaller. And now I've got something that's looking more symmetric. And of course I can write that. I'm taking an expectation of a conditional expectation. That's just an expectation. Right? That's this thing. And I'm going to use this notation Pn prime for this empirical distribution. And Pn, of course, is our old empirical distribution. Right? So what I've shown is that these deviations are not much more than upper bounded, I should say, by deviations between sample averages and independent sample averages. Okay? But if you think about these, in particular these random variables, they have exactly the same distribution. I could have written them in the other order, and I've got something that has exactly the same distribution. Right? I could have written them in any order. I've just rewritten that line, and now I'm putting an epsilon I in here, which is plus or minus 1. I can choose whatever value I like for epsilon 1. And I've got something that has exactly the same distribution here, and so in particular exactly the same expectation. Right? I could choose whatever value I like for epsilon 2, and the same thing is true. Okay, so I can pick anything for these epsilon i's, and I have this equality. I'm actually going to do something else. I'm going to randomize the epsilon i's and pick them to be uniformly plus or minus 1. And I have exactly the same equality, right? An expectation across a whole bunch of equal things, right? Of course, these are our Rademacher random variables, and then we just do a little bit of sort of approximating, right? Once we have this quantity, we can split these pieces, just use triangle inequality and say, well, we've got that piece, and we've got an epsilon I times that piece. And now we can upper bound it by this piece plus this piece, which gives us these two. And of course, that's twice the Rademacher complexity. Okay. So that's the upper bound. You know, everything's relying on the symmetry that we get from the IID assumption. Right, the Z1 through Zn are being IID. Questions? Or, yeah, good.
The only inequality there is this triangle inequality, right? Otherwise it's completely fixed.
Two places. So this triangle inequality is one. That introduces a constant factor. Right? The other place is this one, where we pulled the supremum inside the expectation. Okay, but you know, somehow that doesn't hurt, right? And we see it doesn't hurt from the opposite inequality, and the opposite inequality is obtained just by another triangle inequality that we can get an upper bound on the Rademacher averages in terms of deviations. I won't go through it, but it's really just saying, you know, you can split things by taking expectations in and out using a triangle inequality, and then, you know, everything's kind of small. Right? This part gives you deviations between sample averages and expectations, and this part's small. You can, you know, go look at the slide. It's a very straightforward argument that I won't go through. Okay, so that's the result. I guess this is the line to look at, right? That if we're interested in deviations between expectations and sample averages, maximal deviations across a class, then those things are close to the suprema of the supremum of this Rademacher process across the class. Okay. Probably a good point to pause. Any questions about Rademacher complexity? All right, so let's get back to our problem of losses. You know, the G here has just been, for this part, an abstract class of functions defined on a domain Z. But actually, we care about compositions of losses with functions from some particular class of prediction rules. And you know, for the G, we have that our maximal deviations are bounded by the maximal value of this Rademacher process. And you know, it involves losses composed with functions, and you know, we're interested in the functions themselves and what we can say about a particular class of functions. The L is usually something that we can conveniently get rid of. For classification in particular, it's very easy. So think about the case of two-class classification, right? So our function class F is mapping from images to cat or dog, right? Our Y is those two classes. Our loss function is the indicator for getting it wrong, right? But we can write this as in this sort of linear form, linear in whatever the prediction is, right? And because these things take values either plus or minus 1, you know, if you just think about those having the same sign or different sign, this is saying exactly the right thing, right? It's 1 if they're different, it's 0 if they're the same. So when we plug that into the Rademacher averages, the Rademacher complexity for the loss class, right? This is our loss class for a particular function, f. This is an element of the loss class for this particular f. So this is the Rademacher complexity of the loss, composition of the loss and the function. But we can rewrite the loss in this way that's linear in f, right, for any given y. It's just this 1 minus this product times a constant. And now, of course, we can split that up. You know, this part is just the Rademacher complexity. And this part is just some little order 1 over square root of n thing. Okay, so for classification, you know, we can essentially ignore this loss function. It just changes things by a constant and some small additive thing. Less clear for other loss functions. We'll see we have to work a little harder in other cases. Okay. So I wanted to step through a few tools that give us, for instance, ways to deal with other kinds of loss functions. So in particular, the key thing that I guess we're going to use all of these, but one of the things we'll work with is what happens if we have a Lipschitz loss. But let's step through all of these things. So you know, the kind of mentality behind listing a bunch of these properties of Rademacher complexities is that we can snap together different pieces to build up richer classes of functions and use that to get a handle on the Rademacher complexity of a class of functions by thinking of it as composed in different ways from different pieces. You know, so for instance, obviously if we have a smaller set of functions, then we have smaller Rademacher complexity, just because we're taking a supremum over a smaller set. If we scale things up by a constant, right, then we're just scaling the whole thing up by that constant, right? Because the functions appear linearly in this thing, right? It's a constant times the function that appears in that sum. If we add in a constant function, right? So we have a class of functions and we add in something that's just a single fixed function. It doesn't change things by very much, right? Changes things by sort of 1 over square root of n. So no big deal to take any particular fixed function, right? It's only changing the Rademacher complexity by an additive 1 over square root of n term. If we take a class of functions and consider its convex hull, so linear combinations of functions from that class where the sum of convex hull rather than symmetric. So let's say positive weight linear combinations of functions from that class where the sum of the weights is 1, right? Then that doesn't change the Rademacher averages. And that's because we're doing a maximization of a linear quantity. All right, so if you consider the convex hull, you know, the maximum is going to be achieved at the corners, the boundaries of that convex hull. Okay, so convex hulls don't change anything. And the last one is, you know, thinking about what happens when we have this sort of a class and we want to consider, you know, because we're interested in maximal deviations across classes like this, loss functions composed with functions from some class, then you know, there's a result that says as long as this loss is 1 Lipschitz in the prediction, right, then we don't change the Rademacher averages by much. There's a constant factor and a little 1 over square root of n appearing. Okay, so putting things through a Lipschitz loss doesn't change things. And you know, add in a constant here and we'll throw it in there just by scaling. Okay, so these are there's a laundry list of properties here, and we're gonna see we can apply those to get in a pretty easy way to get Rademacher complexity bounds for useful and interesting classes of functions. All right. So let's look at a very easy example that's, you know, I guess much more focused on the deep network side of things. So deep networks, we're going to think of them as compositions of nonlinear functions. In particular, we might have each one of these layers computed by taking a linear combination, a linear function of the vector input to produce a vector output, so Wi is a matrix. We pass that through a nonlinear map that maps from vectors to vectors, right? And maybe it's the component-wise map where each component is a squashing function like this sigmoid, all right? Or maybe these nonlinear maps are this ramp. They're going to be this max of 0 and that component. So this gives us a ReLU network, right, for rectified linear units. So you know, we could imagine a network that's computed in this kind of a way. The parameters are these Wi's, right? That's what changes the W's in each layer change what's being computed, and we think of these as fixed nonlinearities in the different layers. Okay, so for classes of functions like this, what can we say about the Rademacher averages? Which is equivalent to asking what can we say about excuse me, uniform deviations between expectations and sample averages over this class of functions. All right, so let's think about the sigmoid case first of all, because it's easier. Okay, this is 2-layer, but just because I was lazy, you know, the same result applies with this 2 in particular change to L if you want a result for L layers. So this is 2-layer networks with sigmoid nonlinearity. So this sigma here is has a Lipschitz condition, let's say with Lipschitz constant 1. Okay, I'm making it pass through 0. I guess that's only important for constants. This is no big deal. And I didn't write it anywhere here, but this is a sigmoid function that what else is important here is that this function actually maps to a bounded interval in the reals, right? So it never gets outside of, let's say, plus minus 1. Okay, so that's missing from this slide, but essential for the argument that I'm going to make. Okay, then for such a network, so what is it doing? Here's a bunch of parameters. These VIs are vectors. There are k of them. K's, you know, anything you like. They're as wide as you like. And each one of the VIs has a 1 norm constraint. And then you've got this vector of k output weights. They also have a 1 norm constraint. And we have d-dimensional inputs, right? So the x's are d-dimensional. I guess the VIs are in RD. Then the Rademacher complexity of this class is bounded by b squared times square root log d over n. Okay, so we're paying a price. So the number of parameters can be as large as you like, the number of nonlinearities. We're paying a price in the scale of the parameters. Okay, so the proof is really just piecing together these kind of obvious properties of Rademacher complexity. So let's, starting from the input, we can think about our a particular class of functions that takes you from a d-dimensional input vector to just one component of that vector. All right, so this is a class of size d. And then we can consider the first layer functions before the nonlinearity. Right, these things take inputs and scale them linearly by something that has a 1 norm constraint of b. Right, and we could rewrite that as b times the convex hull of these functions together with their negations, because we've got absolute values here, right? We could be in the positive or negative direction. So we need both positive and negative xi's, and then we're taking the convex hull of these guys, right? Because we have a 1 norm bound, but it's a bound of b, so it's the b scaled convex hull. We've written out what the convex hull is. Okay, and then our class of functions, is, well, we take all of those linear functions, right, the VIs from this class, right, we pass them through a nonlinearity, and then we take another scaled convex hull. So we can write the whole thing as, we've got our class VB up here for the first layer functions. We scale that, we compose that with this nonlinearity, right? And then take the B scaled convex hull, and we have to consider negations again. Right? So this is our original class, and you can see why I'm writing it in this way, right? Because we're going to use all these little pieces to plug things together. And hopefully you get the idea, right? So our class, we're interested in its Rademacher complexity. We can write that as the Rademacher complexity of, this is the same class, it's the B-scaled convex hull of, possible negations of, nonlinear function computed at, and these things are the B-scaled convex hull of the inputs. Okay, so, scaling just passes straight through this linear thing, right? So we get the B coming out here. Convex hull makes no difference, right? The Rademacher averages for the convex hull are equal. So this union of two classes, I guess I never wrote this one down, but that's no more than the sum. To see that, you're taking a max over this, over something in this, and something in this. And down here, we're taking a max over something in this and adding it to a max over something in this. So, as long as these things are positive, we're just getting an upper bound, possibly losing a factor of 2 by doing it. And of course, these are exactly the same thing. Negations don't change anything because of our absolute values. Passing things through our Lipschitz nonlinearity is that contraction inequality that I wrote in a special form for loss functions, but it's true in this simpler form as well. And then just writing out what VB is, it's the B-scaled convex hull of the inputs, possibly negated. Again, the B passes through, we get a B squared. The G union, blah, 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 right? Okay, you get the picture. This is a cardinality 2D class, so let's stop there, right? We've seen we get a log of the cardinality of the class divided by n, all square root for this thing. And so, it's very easy. And you can imagine if you wanted to go deeper, then you get, these factor of 2b appearing each layer, right? So you're raising this thing to some power, depending on the depth.
So question. It seems so insensitive to the activation function. Is this
all we're using is this Lipschitz property. We're using two properties, actually, of the activation function. One is that somehow it's pinned not too far from 0. So that's been swept under the rug in all of this, but if you have things that have a ridiculously large scale, that can affect things, right? So we need that it doesn't take us from something near 0 to something very, very far from 0. So that's one thing. I guess there are three properties. There's that. We're using the Lipschitz property, which appears very explicitly here. And we're using the fact that well, I guess it's implicit. We can think of it as just those two properties, and I'll stay quiet about the other one. Yeah. It'll come up later. I'm not making this up. I guess I am. I've made it a murder mystery now. Yeah.
So by using this bound, basically we are suggesting that if we go deep, then it's harder to generalize because it's like 2 to power L.
Oh, that's right. Yeah. The bound gets worse as we move up through these layers. That's right. The place where we have actual inequalities here, this one introduces a factor of 2. Okay, so maybe there's a in that 2b to the depth that we see, maybe the 2 doesn't belong there, right? And in terms of the b, if you think of the scaling end to end, that's b to the depth. And if you wanted to rescale things, that's inevitable, right? From the scaling law, you have an equality there. Rademacher averages of a scaled class is scaling times Rademacher averages of the class. So that part's also, in some sense, inevitable. If we're considering, exactly this class of functions, we haven't lost very much in that case. But remember what it is that this is equivalent to. It's equivalent to maximal deviations between expectations and sample averages across the class. So we're really using the whole power of that class, or considering the whole power of that class when we think about quantities like this, which may not be relevant to the behavior of an empirical risk minimizer. Okay, so it may be that you can find an empirical risk minimizer that is actually has expectations and sample averages closer than the worst case across this class. Yeah. Another way of viewing that is we could have a class that's much richer than we ever need, right? So this class is certainly contained in some much bigger class that satisfies the class of all functions that satisfy whatever end-to-end Lipschitz constraint this class satisfies, and then things would get hugely more complex. We'd get the dimension appearing in an exponential way for that class. So if we went through and did calculations of this sort. So we're considering something much bigger than we actually need to consider. Okay. Yeah, we saw that. Let's not be too concerned about that. Okay, so that was sigmoid networks. What about ReLUs? I guess the sigmoid nonlinearity. Okay, I'm gonna skip over this. When we're so actually, this slide's referring to a quite different technique from the one I want to show you. So let's skip on to that. All right, so we can use a specific property of the ReLU nonlinearity. So this piecewise linear nonlinearity, we can use a specific property of that to give us a bound on the Rademacher complexity, and this is a nice simple argument for this. So the property is that that we can pass constants through the ReLU nonlinearity. So if you think about this function that's the 0 function to one side of 0 and then identity function to the other side, if you scale inputs by a constant, that's the same as scaling outputs by a constant, right? Because it's a piecewise homogeneous linear function. Okay, so we can scale up the output to have exactly the same effect as scaling up the input. So we'll use that to show this result. It's stated as a high probability bound. Why is that? Yeah, so ignore the high probability statement. This is just an expectation of this supremum of the Rademacher process. So we're just working in expectations. This was corrected and this wasn't, so I apologize for that. So okay, so the Rademacher complexity of this class, which is, I'll explain in a moment, this class of ReLU networks is bounded by something like b to the depth over square root of n. And we could have stopped at L equals 2 and I could have waved my hands in the same way as for the sigmoid case. This network has, it has an F down here for Frobenius and a B for the bound. So we've got a bound on these, the scale of these weight matrices. The sigmoid, the sigma function is the ReLU, so it's a 1 Lipschitz positive homogeneous function. Applied component-wise to its input vector. And these WIs satisfy a Frobenius norm constraint, right? So the scale of these matrices is bounded by B. Okay, so the result is loose in the sense that we're working with a Frobenius norm. There are tighter results than this one. I think the proof is really appealing. Okay, so we have this class of functions, and the Rademacher complexity is like the product through all of those L layers of the scale of the matrix that we get in each layer. Okay, so that's the class of functions, and that's the result. I guess it follows from this sort of step in moving from one layer to the next, where we're saying, fix the input, the sample, x1 through xn, and consider just the conditional expectation averaging out the Rademacher random variables. When we look at the maximum over functions, this is a little confusing having two F's here. This is functions in some class, right, which is the class of functions you can compute up to this point, right? And this is a Frobenius norm of the next linear transformation, this matrix. Okay, so this inequality says, the expected supremum over whatever functions you have from the input to this point, you're maximizing over those. You're maximizing over the linear transformation that you apply before you apply the nonlinearity, and then look at those Rademacher. Not the Rademacher complexity. It's actually a 2 norm here, right? Because we've got a vector valued thing. So we're interested in maximizing the 2 norm. Right? And at the end of it all, we'll get a 2 norm of, the last one of these is the output matrix, which is a row vector. Okay, so the 2 norm ends up being the actual absolute values we care about. But along the way, we're considering scalar vectors. And the inequality says that thing is no more than B, which is the bound on the Frobenius norm, times the corresponding thing for the functions that appeared here. Okay? So this takes us from a result about the functions up to this point in the network to one more layer, right? Functions at the next layer. So you apply this repeatedly, you get this 2b to the number of times you apply it appearing. And then you want to consider what this thing looks like when you write back at the inputs. Okay, which is the simple little inequality for that last piece. Okay, so why is this inequality true? Right, it's using these specific properties of the ReLU. And here's the key. So if we think about our W as having a bunch of different row vectors, right, W1 through W whatever it is, K, right? So F is our vector valued function up to this point, and then we're applying a matrix W that has rows W1, W2, and so on. Then this is a component-wise nonlinearity applied to the components of this vector. We can work row by row, split things up into first component of the vector up to first component of the vector up to kth component of the vector, and we're considering the 2 norms squared. It's just the sum of those things squared. Okay, I've done nothing more than write out what a Euclidean norm squared looks like. But now when we're here, we can use this positive homogeneity property of the ReLU function. We can scale everything here so these guys have unit norm. All of the rows have unit norm. And the scale out there, the scale in the denominator comes out here. Right? We haven't changed anything because we can pass constants through this nonlinearity. Okay? So what's really nice here is that then when we go and look at a supremum, right? So we've got that quantity that we've scaled things to have unit norm here, and the norm just appears out there. Our Frobenius norm here this is a bound on the sum of the squares of all the entries in the matrix. So it's a bound on the sum of these things, right? The vectors, the Euclidean norm squared of the rows. So we can rewrite that as, what's the Euclidean norm squared of the jth row? Let's call that alpha j, right? We need our sum of alpha j's to be no more than b squared. And that's it. That's the only constraint. And these things, of course, are unit vectors. Right? So now we've got, we're interested in an inner product now between something that has a 1 norm bound of b squared and this other thing that we're maximizing. Right? But that's very nice. Just take the supremum over the wj out and consider the inside supremum over these alphas, and we've got an inner product between something that has a 1 norm, no more than b squared, and some particular vector. Right? Of course, we just want to focus on the maximum value of that, the maximum component of that vector. Right? That's this thing. It's the supremum over all the, well, I guess that's this thing. Right? Times the value of alpha 1, let's say, right, which is b squared. All right, so we've gone from, so there's still a little step to do. We have to get through this Lipschitz function. We have to work with the fact that this is a vector, and there are some more details at the end to get this in terms of just the supremum over the functions when we start with a supremum over functions. So we can get this kind of inequality with another couple of small steps. But the heart of the argument is there. We're really able to focus on just a single row of this vector and maximize over that row because of this nice positive homogeneity property of the sigma function. Okay, so that gives us this a result of this form, this 2b to the L divided by square root of n. So a similar form for ReLUs. Probably pause there. Questions? Okay. I wanted to say a little bit about covering numbers, about another notion of complexity and how it relates to Rademacher complexity. We'll see that you can get upper and lower bounds on Rademacher complexity in terms of covering numbers of a class. Often this gives a very convenient way of working with uniform laws of large numbers, particularly when things are kind of end-to-end Lipschitz, right? So you can exploit that sort of property and make a very simple argument using covering numbers. That's often another very convenient tool. And actually, you can get in terms of the kinds of norms, you can get an improvement on the ReLU result that I talked about in terms of covering numbers.
So
yeah.
In that ReLU proof, if I were to replace the activation just by the identity function, right, that also is homogeneous.
Yeah,
But then
it goes away.
But do you get the B to the L again, even though it's all
Sure.
linear of linear of linear?
Sure, because it's linear of linear of linear, but the Lipschitz constant of the whole thing is B to the L, right? So you have that scaling appearing through the whole network. Because remember, we're keeping a uniform constraint of, the scale that I can see from input to output is B at each step along the way.
Maybe then the spectral norm is incorrect.
Exactly right. This is a weak way of a strong way of constraining things. So yes, it's in some sense the wrong norm. We should be working with a spectral norm, and you can get, this is actually the point I was making about when I'm waving my hands about covering numbers, that you can get results in terms of spectral norm, in terms of tighter results in terms of other norms using a covering numbers kind of argument, but not, don't know how to do it using Rademacher averages argument.
So if I've not already forgotten, so you have a bound for, say, these ReLU networks. Now, originally the Rademacher average depended on the data distribution, but the bound, if I'm not mistaken, no longer depends on the data distribution, right? Or
for these cases, right. So if we look at this result, this says, for every probability distribution, there's nothing about the distribution here, right? This is just saying, we have an upper bound that's true for every distribution. So all we're using is this sort of scaling property of the class of functions. So we've potentially lost a lot, right? It may be that we've got a class of functions that can do something very, very rich over here, but the distribution we have never illuminates that part of the space. So, it could lose a lot, even if, uniform convergence is accurately capturing what's going on in a learning problem. We still have an additional source of looseness in these examples. Yeah.
There's only a few inequalities in the argument, so can you isolate where potentially data dependence might have been ignored?
In some sense that. What's that?
Contraction?
Yeah, it's a good question. So the fact that we're not using anything about the probability distribution is saying that really all we're just capturing the kind of scaling of the functions that we can compute with this sort of class, and that's telling us the kind of Rademacher complexity upper bound that we get. It's if somehow you don't use the full power of that, with a particular. Yeah, I guess I'm saying the same thing again, but I don't know of a kind of concrete aspect of this class of functions that you could point to and say, here's where a difference might arise between different distributions. Yeah. Yes, question.
If only we could compute empirical Rademacher complexities, we could find out.
Right, which are concentrated. Yeah. That's right.
Maybe we could actually test it on some simple examples or everything.
Yeah, in the classification case, for instance, computing empirical Rademacher complexities is no harder than empirical risk minimization. It's exactly the same problem. Other questions? All right, let's say a little bit. Oh, yeah, one more.
Do we know, I guess along that line, do we know if these upper bounds are tight, at least in terms of the asymptotics?
Right. So you can. What can we say? So if you for instance keep to the linear part of the ReLU everywhere. I guess as I've written it, that's a little strange because I haven't had an offset here, but imagine, right, that we have an offset, an additional variable throughout. Keep to the linear part. We're computing a linear function in a funny way, but for those linear functions, it's really the scaling that's important, and modulo the norm I've chosen to give you a simple proof. You can't hope to do any better in that case, right? Which is answering a different question too. Is this the right thing when you consider a ReLU network as it emerges from a stochastic gradient optimization procedure? Yeah.
The other component is like you're treating the norm bounds on each layer separately, right?
That's right. Yes. Yes. So this is in some sense an unnatural. Again, because I wanted to present a simple proof. It's in some sense an unnatural class, right? Where we're saying we have a uniform bound across all of these things. On the other hand, you give me a product of.
Right. No, I was more concerned with
you can
how
shift
these
things,
two
etc.
interact. Like W1 might depend on W2 usually.
Oh, I don't understand. What do you mean?
So this is the worst case bound when, like, for example, even for a linear model, like
right.
if they're completely orthogonal, you'll get B power L.
Uh-huh.
But if they're aligned, you get more like B.
Right. So I mean, you can. I'm not sure I understand. You can get a lower bound for the linear case by arguing that actually we can explore the full power that this constraint, this kind of B to the L constraint, gives us on the end-to-end scaling. Right? So you're saying actually we might not be using that much power. Of course, this may be one example where this difference I just described arises. Yeah. Right. Other questions? All right, so I have 5 more minutes. Okay, so I'll say a little bit about covering numbers, in some sense for completeness, but I won't spend very long at it. So, the idea of a covering number is kind of a natural thing when you see that you can say something about finite classes and make the observation that actually, we don't really care about arbitrarily fine differences between functions. Surely we should be able to approximate an uncountably infinite class with a finite set, and that's exactly the idea of a covering number. So we have some set T, and the idea of finding an epsilon cover of this set. We're in a metric space. D here is not a dimension; it's a metric. It's a distance, and an epsilon cover of this set T is a set of points that for which for every element of T we can find some T hat in our cover, some little T hat in our cover, capital T hat, that's within epsilon of it. And the covering number is just how many of those we need if we want to get within, this is a nice center, isn't it? If we want to get within epsilon, right? Okay, and and the intuition is if you want to cover something that's kind of k-dimensional, then you need like 1 over epsilon to the k, right? Vaguely, if it's sort of a fixed scale, then you've got to get this sort of exponential dependence on the dimension, and so often you see the log of the covering number or the exponent in pull out the exponent by considering the log of the covering number. Right, so ratio of log of covering number to log 1 over epsilon. That's the metric dimension, one definition. I guess the asymptotics of that. So that's the kind of picture to have in your head, is how this thing scales as a function of 1 over epsilon to what power. So the log of the epsilon covering number is sort of that relevant quantity. And there are upper and lower bounds on Rademacher complexity in terms of these covering numbers. The upper bound is saying if you consider the square root of the log covering number, as epsilon goes to 0 is the way to think of it, right? The infinity is sort of irrelevant. As epsilon goes to 0, you need a bigger cover to at some point we're at the diameter of our set, right? And we don't have anything else going on up there. The upper bound says, if this is the square root of the log covering number, then the area under the curve is an upper bound on the Rademacher complexity. This is due to Dudley. And the argument is all about approximating things at multiple scales. That's where the integral arises. The lower bound is saying, if you find a maximal area, a rectangle down here, that's a lower bound on the Rademacher averages. Those things could be quite different, right? The integral and the biggest rectangle. And in some sense, that gap is inevitable, right? So this thing is the right thing for maximal deviations between expectations and sample averages. Covering numbers, it could be loose one way or the other. But they're very convenient to work with, and in 1 minute, if you've got a class that you define in terms of some parameters, and things are Lipschitz, right, in terms of those parameters. So if you want to compute a function, then things change in a Lipschitz way. I'm just going to wave my hands. Then it's really very easy to see that you're just changing the scaling with that Lipschitz constant, right? If you can cover the parameters with some number of approximating points, then you can cover the class. And this is hugely convenient in working with these things. And I've said all of that. All right, so that's probably a convenient point to stop and ask if there are any more questions.
Some properties of the underlying distribution and the data to these bounds, because you can have like one structure who doesn't generalize on like random labels, but
right.
Generalize on say natural properties, things like that.
Okay, so I am. So if we actually go back to structural result. If we go back to this result, so if you're looking at maximal deviations, this inequality says we've got the right thing. These maximal deviations are the ones that occur for that particular probability distribution, right? So we're saying for every p, I guess it didn't spell that out, but it should have at the start. For any p, for any g, we have these tight inequalities. And so, the specifics of the probability distribution are baked into these things, because this expectation is over the sample that came, the Rademacher random variables, but also the sample that came from that probability distribution. So if it's, a peculiarity of the distribution, these things capture it. But then when we go to, compute bounds on those things, we may have lost that property, right? Is that what you're asking? Specifics of a probability distribution?
Yeah, partially you answered that, but also like, say if I have some natural images with some labels, and I have like a neural network, empirically we observe that it generalizes well. But now if I just shuffle my labels and have random labels with the same complexity as the number of parameters and stuff, I see bad generalization. So in that sense, how we can use some of these bounds like Rademacher complexity.
Right. So that's a good indication that just considering things like I mean in that example, the scale actually does change, right? When you try to use stochastic gradient to I was about to say train, but to load random labels into a network. The scale does change. So when you're working with even the inequalities that may be loose, they don't capture anything about the natural images, whatever distribution they came from. So things are changing in some sense there, right? These sort of bounds on complexity that you see. But I really think you're in a different realm from the sort of case that we're thinking about here. These sorts of deviation bounds are going to tell you, that the empirical risk minimizer has has true risk. The expectation of the loss no more than empirical risk plus some quantity, right? You can use something like this to say it has no more than the best in the class plus some amount. But actually, that's really based on these deviations between sample averages and expectations. And the examples that you talk about, the sample averages end up being 0. Even when you add noise. So we're going to come to this, in the last lecture. But that feels like a very different regime from the one that's relevant for these sorts of results, because there you're driving the regression loss to 0, even if there's noise in there, right? So that's kind of a different world from trying to get something useful out of a deviation between expectations and sample averages. That deviation should be big, because you have a noisy problem, and yet you're driving the sample average to 0. So for that sort of approach, I think that's in a different regime, and I think that's kind of one of the exciting directions that we'll talk about in later lectures.
Maybe last question.
Yeah.
Could you go back to the slide on the ReLU bounds?
Sure. This one?
Yes. So why choose at the very bottom that constraint on the Frobenius norm of WI less than or equal to
Good question.
as opposed to, say, the product of the norms over all i's less than or equal to b, especially when you've got sigmas that are homogeneous, and so scaling of the weights.
Yeah, but
would that?
But that's the same class of functions, right?
It's the same.
So if I take a supremum of this class of functions, for every function in the class that has a product equal to some value, I can give you exactly the same function computed with a uniform bound on each one. I said that badly, right? If the product of these things is no more than b to the L, then imposing this uniform constraint is just shuffling the scaling throughout the network using this positive homogeneity property. So in this case, it doesn't change anything.
Okay, great. Let's take a break until 1:45, and then we'll have the open comments.